To move data across the globe, we rely on electro-optic modulators. These devices act as translators, converting electrical data into pulses of light that can travel through fiber optic cables. For decades, the industry standard for this translation has been an inorganic crystal called lithium niobate. It is the workhorse of our current telecom infrastructure. This chart shows exactly where the problem lies. On the left, we see global data demand rising exponentially. On the right, we see the performance of lithium niobate. It works flawlessly at lower frequencies, but as bandwidths push past 40 GHz, the crystal's signal quality hits a hard ceiling and degrades rapidly. No amount of engineering can bypass this limit. The 40 GHz ceiling is hard-coded into the physical atomic structure of the crystal. Hardware engineers are now facing a difficult choice. They either accept these capped data speeds, or they abandon the most reliable material in telecom history to find a faster alternative. The leading alternative is a class of experimental materials known as organic nonlinear optical polymers. These polymers are capable of supporting bandwidths well over 100 GHz. On paper, their performance is staggering. The electro-optic coefficients of these organics can be up to 10 times higher than legacy inorganic crystals. But choosing organics requires a significant compromise. You are trading decades of proven, rock-solid physical reliability for extreme speed. The precise molecular structures that give organic polymers their speed also make them notoriously unstable. Over time, and especially under heat, they are highly prone to thermal degradation. The decision for the industry comes down to weighing raw, fragile performance against long-term commercial stability. To understand why organic materials are so much faster, we have to look at how they react to electricity. Inorganic crystals like lithium niobate change their optical properties by physically shifting heavy atomic nuclei. Moving that mass requires high energy and takes time. Organic polymers use a completely different mechanism, relying on a structural feature called pi-electron conjugation. Instead of moving heavy nuclei, organic molecules use a smeared-out cloud of pi electrons. They react to an electric field instantly, lowering the dielectric constant. This instantaneous response allows perfect optical phase matching with an incoming light wave, easily pushing past the 100 GHz bandwidth barrier. This table shows the massive advantage this provides. Looking at the second-order coefficients here, lithium niobate sits at 40, while a specific organic molecule like MNA reaches 250, with a fraction of the dielectric constant. This means organics can drive communication devices using less than 1 volt of power. However, that exact same extreme electrical sensitivity is precisely what makes them chemically volatile. Growing single inorganic crystals is an arduous, rigid, and high-temperature process. Polymer manufacturing, on the other hand, is highly versatile. This diagram shows a common manufacturing approach called guest-host processing. Here, the active organic molecules, the guest, are dissolved directly into a transparent liquid polymer matrix, which acts as the host. Being in liquid form offers a massive manufacturing advantage. This solution can be cheaply spin-coated onto flexible substrates or integrated seamlessly into intricate silicon photonic chips where bulky crystals could never fit. But the guest-host method introduces a significant trade-off. The active guest molecules have limited solubility within that liquid matrix. Because they don't dissolve endlessly, you hit a strict physical cap on the concentration of active molecules you can use. This ceiling inherently limits the overall nonlinear optical activity of the final cured film. Organics win decisively when it comes to cheap, flexible processing, but engineers must accept strict limits on the maximum optical density of the resulting device. Even if you achieve the perfect concentration, you face a structural hurdle. In their natural state, organic chromophores arrange themselves randomly in anti-parallel pairs. This alignment completely cancels out their optical effects. Corona poling applies heat and a high-voltage electric field to force molecules into parallel alignment, freezing them in place as temperature drops. However, poled polymers suffer orientational relaxation. Over time and under thermal stress, these molecules naturally relax and revert to a randomized state. As the molecules scramble and lose their perfect alignment, the device permanently loses its optical properties and fails entirely. Chemists can use cross-linking techniques to physically tie the molecules down and slow this decay. But adding those chemical bonds significantly increases optical scattering losses inside the material. Ultimately, an organic device's entire commercial lifespan depends on maintaining a highly unnatural alignment that is constantly trying to unravel itself. With these constraints in mind, we can map out exactly which engineering disciplines can actually tolerate the trade-offs of organic materials based on their operating environments. Consider the commercial telecom sector. Mass-market network deployment demands hardware that can survive in harsh, remote environments with near-constant heat and absolute uptime requirements. Because of that thermal reality, commercial telecom must reject organics for now. They have to stick with lithium niobate to guarantee decades of zero-maintenance thermal stability. But the next-gen hardware space is completely different. When designing terahertz imaging systems or wearable sensors and on-chip silicon photonics, bulky inorganic crystals physically cannot fit the architecture. In these scenarios, developers are forced to adopt organics. They must leverage the advantages of spin coating processability, while heavily investing in advanced chemistry to prevent molecular relaxation. The reality of organic nonlinear optical materials is that they will never be a simple one-to-one drop-in replacement for inorganic crystals. This industry is moving away from brute force crystalline durability toward a strategy centered on molecular engineering. The rule of adoption is clear. If your device's thermal environment cannot be strictly controlled, you must stick to inorganics. But if your project absolutely requires bandwidths over 100 GHz and seamless microscopic chip integration, the age of organic photonics is already here. The raw speed of these materials is proven. The final engineering hurdle now lies entirely in keeping those volatile molecules perfectly in line.